So what we're going to do today is finish up the last part of kinetics. So this is our last quick review and the last section of the physical part. We're going to continue on from there into our intro organics as we're transitioning to the second half of the course. Now, just a couple quick reminders. Midterm 2 is coming up. Midterm 2 will be, does anybody remember the date? Off the top of my head, I do not remember. It is not this week, hooray. We will start having messaging of that coming up. The reason we want to remind you of that now, midterm 2 will be in person. So if you've been attending virtually or other components, if you've been watching it online, you will have to do midterm 2 in person. So we will have updates on that coming up in the next couple weeks. Midterm 2 will cover everything from delta G naught and Q all the way up through kinetics and the first part of organics. So it's this bridging part at this point. Again, we'll give you the cutoff date once we cover that part too, but it will be in the weeks ahead. Yes?
In person, in class, or outside of class?
In person, outside of class. So this will be, we have a block of rooms that will all be written during a sort of a standard piece. It will also have the same kind of format as last time, which means there's an individual portion and then a group portion. The group portion will be done in that section though, so it's not the next day. Yes?
Can we like preemptively?
Guys, 1 second. Can everybody, whoop.
I don't know if this is your domain or not, but I know data science, like Data Sci 100, which I feel like there are multiple people in this class that are in. It also has a midterm the same day at 7:30 p.m. And that was a conflict this last midterm. And so if you put it at 7:30 p.m., it will also be a conflict for this upcoming midterm.
Understood. Again, I have to check back into this part. Again, the reason we saw this one wasn't big deal because we had the window, right? That's not too bad. I do understand that coming back into person, these will be a part. We're doing our best. The challenge we have is booking on campus in terms of rooms is highly, highly, highly difficult, but we will absolutely try to make sure we stay clear of any other ones. All right. So, over the break, you guys were released a couple of new pieces of stuff to pay attention to. You had the opportunity to participate in a learning study program. This was watching a couple of videos, interacting with them, and learning how to do IUPAC naming. That part is closed. Those videos are still available, so referring back to them is something we expect you to do. We're going to be doing a little bit of IUPAC naming in class. We'll practice it, but we're pretty much going to be doing the operational side of that. In other words, executing and doing the naming is in class, meaning that we are assuming you're going to use the videos as your primary tool to teach you and fill in the gaps. So that gives us more time in class to practice how to apply it, less time in class walking through the individual specific rules, okay? This is better for operational. Second thing too is we have the organic naming assessment on. This is just like the acid-base assessment, infinite times, infinite attempts, we only keep your highest mark. So this is meant for you to, again, go practice operationally how to do IUPAC naming. You have right up until the midterm to complete this as well again. So you have lots of time, but make sure you budget your time accordingly. So where we left off was introducing the concept of the Arrhenius equation. Remember, the Arrhenius equation is our last piece of kinetics. We've talked about now how to talk about reaction rates. We've talked about multi-step reactions, the slowest step, and talking about how the barrier is the thing that matters. Last thing we discussed last time was catalysis, using a catalyst to speed up a reaction. How did a catalyst speed up a reaction? What was the mechanism, or why did it make that possible? If you had to articulate, yeah. Exactly. It reduces the activation barrier. It does not change your delta G naught. It doesn't change the overall thermodynamics of the reaction. It changes how fast, or the barrier to get over the transition state. It does this by providing another pathway. So this is your third way to speed up a reaction, is with temperature. Temperature can influence our K. Our reaction, our rate constant K was something that we said is specific to a reaction. It does not change. However, at different temperatures, the reaction will be faster. This is the behavior that actually provides that. So if you're running the reaction at a different temperature, you can use this equation to figure out what happens to K. Now, as we talked about last time, we have these parameters. K is the rate constant. That's what we've been discussing. T, capital T, is our temperature in Kelvin. R is your universal gas constant. That left these last two parameters that Arrhenius came up with, A and EA, as specific to a reaction. EA, you can think of that as the minimum energy required. It's related to, it's not exactly the same as delta G double dagger, but in the same idea. It's your speed bump. Your A, the frequency factor, this was sort of an efficiency. It's a fudge factor that basically says all transition states do not have the same geometry. We're not going to go into any more detail to that other than to recognize A will change with specific reactions. Every reaction has its own A value and has to be extrapolated. So what we have here is this assembly. K and T are the two variables. What we don't have is the specific A constant, EA constant. So what we can do is, once again, like the Van Hoff plot, like these other cases, if we can linearize this or put a linear relationship between them, we can now extrapolate these values. So our Arrhenius equation up at the top, by taking the natural log of both sides, we now get something that is starting to look like the equation of a straight line. Here, the slope minus EA over R is our equation of our straight line, as long as we're graphing ln K on the y-axis and 1 over T on the x-axis, where the intercept is our ln A value. So we would use a series of different K measurements at different temperatures. That's what we actually go and do experimentally. We plot this value, and then we can use the slope and intercept of that straight line to extract EA and ln A. So this is the main application. We sort of go through this part. Like we said before, if you have a graph that looks like this and a graph that looks like this, which one of these are you going to expect to have a smaller EA value, A or B? A or B? Everybody, come on. This is Monday back after the break. That's right, it's B. The reason why, remember, your slope is directly proportional to EA over R. R is your constant. So a bigger slope, bigger EA value. They're going to be negative. Negative slope is a positive EA. And just in general, too, that's one of those wacky things. There's no such thing as a negative activation energy. Why would that be? What would it look like if a reaction had a negative activation energy? What's that, sorry? Yeah, there's no barrier anymore. Like, what else, how would you describe that also, too? A negative activation energy...
Take energy away to make the reaction.
Completely non-physical. Yeah, what you're saying is somehow by putting things together, there's nothing holding it back at all. The transition state is actually down in energy compared to where you are. That sounds more like an intermediate, not a transition state. Remember, transition state is the apex as you move over this free energy curve. If something had to go down in energy to it, it's like you're moving from a transition state to an intermediate. So that's not physically possible. The last thing we have to do is calculations relating these ones. So this is a very common type of a question that you can encounter. If you are given some reaction where we know the activation energy, we've solved it somehow, and we know a temperature we're running this reaction at, what we're asked to do is figure out what would happen, or how would the K change, the rate constant, if I were to increase the temperature. In this case, we're asked how to increase the temperature. How far do we have to increase temperature in order to double the rate constant? So I'm going to come to this one here. This is the final answer we're going to come to, but let me walk through the full sort of calculation. What we're dealing with here is a case where, remember, our equation is ln K is equal to minus EA over R, 1 over T, plus natural log of A. This is the explanation that says if I have some variation between K and temperature, this is how these will behave with each other. Now, we've been given an EA. The activation energy from the question was given as 100 kilojoules per mole. We don't know the delta T. That's the value we're saying is if I start at some temperature, my temperature initial, Ti, is equal to 298 Kelvin, and we have to move to some T final, which we do not know. We're increasing the temperature in order to speed up the reaction. We're also saying that during this point, the reason, or the target we're saying here, whatever the rate is at rate 1, we're trying to go to some final rate, rate 2. We're starting at whatever the rate is initially, and we want to double that rate. So the equality we've said here is that here, rate 2 is equal to 2 times rate 1. If the rate is doubled, what does that mean about K? If we're targeting the rate has to be 2 times, what is K going to have to be? Also 2 times, right? They're directly proportional to each other. So this information means that whatever K1 is, let's say K2 is our final, must be equal to 2 times K1. Our faster rate must be double the slower rate. So that's how we encoded these pieces together. So once again, it looks like it's almost there, right? We have this equation. We know we could say, all right, I know K1, I know temperature 1, I've got EA, but if you look directly at this, you're missing A. You do not have an A value, so you couldn't just plug in values, solve for maybe K at one temperature, and then try to double that value, and then solve for K at another temperature. What we have to do is look at the equality between these two and see how they change. So let's go back to the graph. Remember, the graph that we're plotting here, an Arrhenius profile is saying here is ln K and our 1 over T, right? And a typical plot will have a negative straight line, where here the slope of this line is equal to our minus EA over R. Now, most importantly, the slope. What is the definition of slope? Slope is blah over blah. Rise over run. What is rise? What is run? Yeah, rise, right, is your y value. Run is your x value. So what we're saying is some change in y will correspond to some change in x. I only need the slope in order to predict that. So you can think of it, right? Slope is equal to y2 minus y1 over x2 minus x1. In this case, your y values are ln K2 minus ln K1 over x values 1 over T2 minus 1 over T1. So all I'm doing is saying, look, slope is just your differences in x, or differences in y over difference in x. My y values, my x values are depending whatever I'm processing. So I've got a re-expression for my slope that now only depends on my k values and my t values. And that is all equal to EA over R. This is equal to minus activation energy over R. Now it's starting to look like this is tractable. We have 2 different temperature values which we're trying to evaluate. We have R, gas constant. We have EA. And we have some relationship between those. We don't know numerically what K1, K2 is, but we know that if K1 was equal to 1, K2 must be 2. It's double whatever that value is. So we can use an indexed value to just say, okay, K2 I'm going to define as double K1. So if I rearrange this, I'm going to redraw this point out. So once again, minus EA over R is equal to ln K2 minus ln K1 over 1 over T2 minus 1 over T1. Rearranging this, I can show this as ln K2 over K1 is equal to minus EA over R, my slope value, multiplied by 1 over T2 minus 1 over T1. So this is just algebraic rearrangement of the equation up on top. The reason I'm putting it this way is I have my K, I have my EA. I'm trying to sort of extract this point here. So I'm just trying to make it into a more simple fraction. So this is a common equation. This is something you should pay attention to, because what this equation very handily does is it allows me to predict any K given a difference in temperature, or given some difference in K, what is the difference in temperature I need? It allows me to go back and forth between these two very usefully. Most importantly, you don't need to touch A. Just knowing the activation energy in this equation allows me to go between those parts. So in this case, remember we said K2 is equal to 2 times K1. So I'm just going to redefine this in terms of only K1, assuming it's equal to a value of 1. That's ln 2K1 over K1 is equal to minus 100,000 joules mole over R 8.314 joules mole Kelvin. And then our final term, 1 over T2 minus 1 over, and our initial temperature was 298 Kelvin. So we now have an equation that's set up to allow us to evaluate and solve single unknown. If we assume K1 has a value of 1, K2 is double that value, so you could just evaluate this as ln of 2 over 1 is really all you're actually sort of doing. If we push this all through and solve for T2, that should give you the value that we just fixed out to. T2 here should solve out as 303 Kelvin. In other words, if we started at 298, given this particular EA, this activation energy, raising the temperature from 298 to 305 will double the rate of this reaction. How much you have to heat a reaction up in order to double the reaction will depend on that barrier. Bigger barrier, you're going to have to go to higher temperatures. Smaller barrier, little changes in temperature will lead to much faster changes in rate. But that's how you push this part through. So again, that's my longhand version of it here. The full description and the derivation are also on your baseline slides. Once again, from the top, this is your rise over run, and the equation that helps you get to here, so this is what we derived, and the final calculation through it, okay? Most importantly, again, this is one of those cases, if you're dealing with R, your value of energy is in kilojoules, R is in joules, make sure you match those parameters. Any questions on this? Yes?
So this is just the same as assuming that K is the same for both 2K and K, right?
Well, what we're saying is, remember, the question is, I want to double the rate of reaction. I don't know what it is, but I'm going to something that's 2 times that value. So if I know K1, whatever it is, I'll call it a value of 1. The final K, my K2, must be 2 times whatever I was. I could call the first value 50 as long as K2 was 100, as long as that relationship is set, right? So I can arbitrarily put any number I want in here because what I'm saying is the relative change in K must be 2, right? That value, something over something as a product, K1 will cancel, right? It's just ln 2.
Right. I was wondering about A.
About what?
About A.
Yes.
So we assume that A is the same for both.
It has to be, yes. This is the same reaction. All you're doing is heating it up. So the A value, you're doing the same mechanism. It's going the same way. It's just happening quicker because there's more energy. But yes, absolutely. As long as this is the same mechanism, A must be constant between both. Yep. Any other questions? Okay. So one last note on this. We're talking about the Arrhenius profile. This is the most common one for people to start using. Arrhenius was the first guy that related activation energy, the barrier of the reaction, to how fast it goes. He recognized that not all reactions had the same barrier. Not all reactions had the same A value. And this is how he began to categorize the world, right? He started to figure out that certain classes of reactions had very similar activation energies or very similar A. It was suddenly a way of looking into reactions and seeing that even though they look totally different, reactions with similar fundamental constants actually follow similar mechanisms. And this is what we'll get to as we start to move to the end of the organic section. We can start to actually bin things together that even though molecules look totally different, if things like these constants are the same, it means that the shape of the transition state may be common, even if the molecule looks very, very different. The point is, though, activation energy is more closely related to only the delta H double dagger, the enthalpic part of your transition state. There is another way called the Eyring plot, which does the delta G double dagger, and that's something you guys will learn in upper years next year. That's the end of phys chem. That's the last part that we're going to talk about this. I know everybody's, yeah. But again, this is where we transition off. We've now got ways of quantifying and measuring the reactions that we're dealing with. So, as we kick off, slide deck 7, this is the organic portion now. So what we're going to start off with is we need a common language to talk about. Yes?
Just a quick question. So with the graph we're looking at Gibbs double dagger, where does activation energy look like?
Good question. So the question is, we are familiar with, we've drawn this plot where we're saying here's Gibbs free energy versus reaction coordinate. On here, we say I have a starting material, I have a product. This value here would be what? What do we call that value? The difference in energy between starting material and product is my delta G naught of the reaction. To the transition state, we have our profile, and we say this value here, that's my delta G double dagger, right? Activation energy is related to this in the same way that delta G double dagger is equal to, if I had to expand it to relate delta G to delta H, what's the rest of this equation? Delta G equals, right? Delta G equals delta H double dagger minus T delta S double dagger. Activation energy is kind of this part of delta G naught. So activation energy, you can think of it, EA is related to this gap right here. It's related to this. It's kind of proportional to EA. In other words, if EA gets bigger, delta G double dagger is getting bigger, but delta G is the whole enchilada. EA is just the delta H double dagger, not talking about the delta S part. So you can think of it as a piece of it. It just means the reason why this prediction doesn't work so well, obviously this value here is going to have a bigger impact on temperature. It slides as temperature changes, okay? All right. Embedded in there, not quite the same thing. Okay. So a couple of helpful things as we move on to organic. Organic chemistry, the thing that makes organic chemistry so difficult is it becomes more abstract. Up until now in Phys Chem, we've been talking about numbers, math, algebra. The different representation, we're talking about what molecules look like, and only until very recently, we didn't have very good even pictures of what a molecule was. So the language of organic chemistry is a way of describing matter using a certain set of rules, how it reacts. The number one thing that helps you with this abstract shape, which is a big chunk of what we start talking about, is these molecular model kits. Now, I really, really like, specifically, I have tons of these guys, the HGS sort of systems. I will use some of these. I can give you guys other recommendations. You do not need these. You can use marshmallows and sticks are okay. Anything that gives you the ability to physically handle molecules. If you don't like the physical one, there are also digital ones that help you too. You can actually, there's a couple online tools that let you build molecules in 3D space and turn them. There's a couple of really good iPhone web apps and stuff to do augmented reality as well for some of this. Point is, you need a tool to start helping you turn these molecules in your mind, because a lot of the stuff we're going to be talking about have visual recommendations. As we mentioned before, there's the organic nomenclature assessment. It's going to open up on Thursday. It's going to close. Oh, no, it's already open. Woo. Opened last week. It's closing 5 p.m. March 20th. So you have many weeks to do this. Once again, this is 2% of your final grade, just like the acid-base assessment. You have unlimited times, unlimited trains. Do not waste to the last minute, because not only that, the purpose of the organic nomenclature assessment is so that we come up with a common language to talk about molecules. A lot of what we're going to start off with is really more like grammar and syntax than it is just about chemistry. We have to come up with a common language set. So that's the first thing. What we're going to discuss as we go through this is rules for discussing molecules, why they work a certain way, and making those rules work for you. Again, I will teach you how I learned these things. This is what made sense for me. But because it does have this contextual side to it, this may not be the only way. This is why discussing with other people can be really helpful. Practice is a big thing. In other words, going through the problem sets as you've been doing, get into a regular routine. Do not try to cram on this. This becomes very, very difficult. At the last minute, you're like, wait a minute, what's carbon? Very difficult. You know, we need to build up to this point, so it's repetition. Careful notes, that's the stuff in class. Reading through the books, the practice problems are critical for this, and especially the problem sets. Again, this is all about repetition. If you have issues, come and talk to us. We can definitely point to certain things. The number one thing I usually try to assess if somebody's having problems with organic chemistry is, what do you really get right now? Where are you missing that gap, and how do I align you? Oftentimes, it's one or two misconceptions that once we get that part cleared up, you've got a common base. Do not look at the answer key. This is the absolute worst thing you can do as you work through this, is you go into the problem set. It's like, how do you name this? You go and look at it, look at the answer and go, oh yeah, I totally would have got that. That's, yeah, not a problem, and move on. It's about practice. And more importantly, Especially, the exam will now include physical written molecules. You will be asked to draw things in line bond structure. That has muscle memory. Doing that correctly requires you to physically draw things. So get down with a piece of pen and paper here. All right, now the fun part. Organic chemistry is as new as 1700s. Does anybody know where it came from, besides what I'm kind of babbling about this? Why do we call it organic chemistry? Any guesses?
The molecules only consist of carbon and hydrogen, which are found in all living creatures.
Exactly. It was considered at the time that chemistry was known, things were made of stuff, but there was a really hard line that was drawn between stuff that made up stuff that was living and stuff that was made up of stuff that was dead. Rocks were not made of the same stuff that people were. There was a line there saying that the fundamental molecules had to be different. And that's sort of true, but the bigger problem was there was this idea that molecules that made up living stuff had a vital essence which made them living, that could promote life and could be eaten. This is sort of back to the thing, if you eat a rock, it doesn't really help you out. Eat something else that was living, your body can metabolize it. So there was a line divided up that said that there was a component of this. The problem was with this vital force kind of idea was that Wohler came along in 1800s and he disproved this. They took a molecule which was unambiguously determined to be an inorganic molecule, ammonium cyanate. This was something you could isolate from an inorganic reaction. It came from rocks. It was definitely considered dead. And he converted it to urea. Urea is definitely a living molecule. It was something they were able to isolate from living things. So this crossed the boundary. This pulled back the veil that said that, okay, we took something that was not alive and we made it into something that should have been part of the living world. This was equivalent to the moon landing because it fundamentally broke down the concept of how matter was supposed to work. This meant that we now had the ability to look at the periodic table, the atoms, and actually do interconversions. Organic chemists became masters of basically the architects of matter, the ability to look at something and say, I wish to build this. So it became looking at the rules of interconversion of molecules. Now, organic chemistry does focus. This, we like to joke that here in red, this is the organic chemistry periodic table. The rest of it's just fruit. It doesn't matter. It's really carbon, hydrogen, oxygen, nitrogen, right? That's the big, big, big stuff. We have a little bit of the halogens. Those are important. Phosphorus, sulfur, those are important for catalysts. But we really focus on this kind of core piece. Carbon is awesome because it has, what's the valency of carbon? How many bonds can carbon form? 4. Hydrogen forms? What about nitrogen? Okay, our valence is awesome. This is good. Did somebody say 5 for nitrogen? 3? We'll cover that over. Point is, carbon, if you count up left to right, hydrogen can bond to one other thing. Next group over can bond to 2. Boron to 3. Carbon to 4. Nitrogen, you begin to get lone pairs, and you start counting down again. 3. Oxygen is 2. Halogens, 1. Carbon has the most ability to bond to other stuff, which gives us the most variety. Carbon can bind to carbon, and carbon to bind to other things. So you can get infinite number of characteristics. Just with this basis set, you can come up with billions of individual molecules, which gives us a very, very wide canvas to paint. The simple fundamental biomolecules we usually talk about, DNA, sugars, and peptides, these are all polymers. These are repeating structures, all made up of just carbon, oxygen, nitrogen, and a little bit of sprinkling of some other stuff too. It turns out that other stuff is what differentiates, which causes huge differences in structure, but this is mostly what everything is made up of. Universal currency too. It means that things that are living can eat other things that are living, and we can use that stuff for us, right? It's a common currency of material. I come mainly from the pharmaceutical space. This is where I mainly play. It's looking at these molecules and figuring out how do we assemble them and how do we make them work with other biological systems. The complexity can go from very, very simple. You look at aspirin. Aspirin is one of those molecules we kind of laugh at now because it's so old, we've known it forever, but it was revolutionary. The ability to go to something that was in a plant that folklore said, hey, eat this plant and you will feel better. Isolating that material, being able to create it from just raw petrochemicals into the same molecule was revolutionary. And we continue to do that now. Does anybody know Tamiflu? Do you remember this? again, this is where the world is moving a lot faster. The last pandemic we had, does anybody remember H1N1? H1N1 was so scary because it was a crazy, crazy deadly flu. Tamiflu was the molecule that was cited as a neuraminidase that could potentially target it. The problem then, as is now, as we sort of talked about for what's happened here, Tamiflu has to be isolated from a starting material that you get from a plant. And it turned out that at that time, they knew how to make Tamiflu, but if they had to make enough to cover everybody, they would extinct this plant many hundreds of times over. So yeah, we could make this raw material, but in the course of about 2 weeks, this became the worst molecule in the world to try and make. Organic chemist was called back in to figure out how do we make it from something else. Same molecule, new strategy, and that's really what we end up doing. So, the most important thing about organic chemistry is structure. How you put the molecule together. One of the things that I got into organic chemistry, I had a biochem teacher in my first year. Have I told you guys the story about why I went into chemistry? So I chose to be a chemist, actually a biochemist, because I'd seen the movie The Rock with Nicolas Cage, best actor of all time. Nicolas Cage in The Rock is a biochemist, and he's a pretty badass character, and that was my full basis for my major decision, nothing else. I do not recommend doing it. I literally never thought more of that. The second reason is I had some phenomenal mentors. I had a biochemistry prof that came in, and he held up an apple and a rock, and he said, these are basically made of the same stuff. It's all about order and arrangement. Structure matters. How you put your molecules together changes their function. The function comes to what we call the functional groups, the parts of the molecule that are not carbon. So you can kind of start to think about molecules where carbon is the fundamental backbone, the presentation of the groups. Those little other things that I kind of gloss over, oxygen, sulfur, phosphorus, that becomes the bits that actually do things, that handshake with other molecules. The reactivity is important because this is how we move one molecule to another molecule. How we change one structure to another one. How do I install an oxygen when I want an oxygen in one place? So these are your 3 levels. Now we're going to focus very heavily on the first 2. Structure and function first, and we'll move to reactivity as we get to the end of the course. So organic molecules defined by their functional group, that's what they contain. So you have to be able to identify common functional groups. They also have a very specific 3-dimensional structure. Their shape really matters. The same collection of atoms in a different shape is fundamentally an entirely different molecule. There's also this other problem of isomers. Has anybody heard the term isomer before? What does it mean?
Isomer, isn't it the different organizations of atoms? Or the different
Absolutely. Same compound, so carbon, nitrogen, oxygen, the count is the same, but the assembly is different. So I have, fingers, toes, things like that. The assembly of that point changes fundamentally what it is, but made up of the same number of carbons, hydrogens, oxygens. The molecular formula is the same. We have different levels of isomers, different classes of symmetry. You can think of this as familiar relationships, right? So you have very distant cousins. You also have siblings. You also have twins in some cases. So small changes in the molecule, we have to rank them differently because that similarity in structure mean different things. And finally, reactivity. So we're going to focus primarily on this top part for the next couple of weeks. This starts with our naming. So back to why does structure matter? Does anybody know what this molecule is? No? It's all cool. That's epinephrine. Does anybody know that name? What is it?
so it's epinephrine. It's a neurotransmitter
Yeah.
that you use. It's basically adrenaline.
It's adrenaline, exactly. This is the thing that gets you through your exam, right? It's a neurotransmitter. We use it primarily if you've had an anaphylactic attack. That's its drug form. It's not a late-night study tool. I do not recommend it. If you guys have seen Pulp Fiction, the stabbing through the heart scene, ta-da, that's adrenaline, that's epinephrine. But look at its structure. If you had to sort of talk your way through what this thing is, what would you call the pieces here? If you had to sort of name what was kind of going on, what's that?
Carbon.
Well, carbons, yeah, but that assembly of carbons that looks like a stop sign is what? That's benzene, or it's an aromatic ring. It means something. Having the specific function is a specific point. What is this? Carbon with an OH is a hydroxyl or an alcohol, right? If you have this carbon with a nitrogen, some other carbons on it, this is a, getting some, it's an amine. The individual pieces of the molecule mean different things, okay? So this one, pseudoephedrine. Does anybody know pseudoephedrine? Yeah? What is it for?
Making meth.
Besides making meth. Yes. I'm going to get so shut down one of these times. So, pseudoephedrine is an antihistamine. We use it primarily as if you've had a cold, if you have a lot of congestion. It can help you to sort of help with your mucous membranes. It helps to dry up that point. That's usually what we dose it. It's also, who has taken way too much pseudoephedrine because you've had a cold? Have you had a chance to sleep after you've done this? It is a stimulant in the same way, similar to ephedrine, but not nearly as much. You can dose yourself in this. As a fun part, my graduate school molecule was a version of pseudoephedrine which actually bounded really, really tightly to lipophilic things. I messed up during a synthesis making that compound. I did not sleep for a week because it was just as powerful as pseudoephedrine, but it lasted forever.
Did you start hallucinating?
Only because of lack of sleep. It was not a good time.
Why did they make you take it?
It was not made me take it. Jason is a very clumsy graduate student that's banging around in the lab and then accidentally exposed myself to it. I was making up at that point. I was so tired and so focused, I was trying to scrub the magnetism off of magnets. Like I was sure that they were still dirty because stuff kept sticking to them, right? Anyway, the last compound, this is methamphetamine. This is not what you want to take. And then again, now you look at this. We've said this before. You may have heard it. Oh yeah, pseudoephedrine makes meth. Look at that. You're different by just one OH. So yes, that's why people use pseudoephedrine as its precursor. It's really similar structure. But also think about the difference. We happily go to the pharmacy, you can buy pseudoephedrine. You should not go to the pharmacy and buy methamphetamine. The difference on your body by one oxygen is remarkable. Even more thing too, does everybody know what's called an enantiomer? I promise you will. This molecule, what does it mean? See that carbon right there, that CH3, that's poking towards you? What does that mean? What am I talking about if I do that? The CH3 with that wedgy, darky structure there, what does this mean here? Yeah, we're saying that methyl is not flat in the page, it's actually sticking out towards you. It's a three-dimensional representation on a two-dimensional surface. That is one geometry. That's like your right or left hand. It is one shape. If you change that methyl from wedge out to wedge back, it does nothing. This is actually, I know, this is one of those super, super cool things that if you do that, that methamphetamine will stop glaucoma. It actually stops addiction. It is a massively powerful, useful molecule. That's not. It's all down to the presentation of a single methyl. This is why I love doing this, is it's a puzzle. This is the best Wordle game you've ever played. So, function and structure. Where you put the groups and what those groups are is what determines everything about biological activity, which means you've got to get this right. If you propose a reaction that just happened to make mostly pseudoephedrine and 40% meth, not something you're ever going to go to market with. I mean, are you in the Sauter Business School? This is not a Shark Tank moment. All right, so most important thing about structure. Yes, sorry. Okay. If you guys haven't noticed, I like this. This is my jam. I love organic chemistry, and I'm really excited about this, so I apologize. All right. Number one, you guys have already experienced at least some of these things. So by clapping, who's seen three-dimensional representation by ball and stick molecules? All right, how about condensed structure? Lewis structures. All right, everybody's seen these. These all suck. Because, no, think about it. We use each of these for different reasons. We're trying to communicate pieces of information in a condensed package. Condensed structures Why would you use those? Why would you choose to use them? What's that? To tell you what chemical it is. Yeah. It's very information poor though, right? CH3, CH2, it's hard to roll off the tongue. Doesn't tell you exactly the molecule. Also, as we start adding atoms to it, it is not ambiguous anymore, or it is ambiguous. It's not disambiguous. It's not identical. There are many different ways to start putting together molecules with that information. It's like a molecular formula, not enough to tell you what you're dealing with. So condensed structures are light, they're portable, but they're not really information rich. But that's where we start, a counting of molecules. Lewis structures, why would you want to use the Lewis structures? Lone pairs, what else? Bond descriptions where you have double bonds, right? Lewis structures say that as long as the world follows the octet, we can start to figure out connectivity. So that molecule up at the top, we don't see anywhere about where double bonds might be. Condensed structure doesn't tell us that. Lewis structures start to show you that, there's lone pairs in these positions. We've got a double bond on this oxygen. But this is the dumbest way to draw a molecule, in my opinion. Molecules are not flat flies that hit your window of your car, right? It doesn't tell you about three-dimensional structure, and more importantly, what I talked to you about geometry, like enantiomers, you can't show that in this representation. 3D ball and stick, this is getting better. This is starting to look like how molecules look. These balls of energy, these sticks, the three-dimensional structure. The problem with them is, if you had to draw one of these on your test, your entire test would be one molecule. Just color, 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 color. It's not a light, efficient way to talk about different things. It's very complex and very detailed. So too far about the structure. So what we really start to focus on are these guys, line bond and wedge dash. So who's seen these guys before, yes? Okay, this here is mostly what we're going to focus on. This is a light form that gives you more information than the other two, but still not quite as far as the perfect 3D representation, right? When we talk about wedge dash structure, we're informing you about what comes towards you, what goes away from you, where those structures are. What does this mean right here? What is that atom? That's what? Carbon. Here? Cool. How many hydrogens are on this carbon right here? 2. In this structure here, this atom is what? How many hydrogens are on that carbon? 2. There are still 2. These are just the same structure drawn in 2 different formalisms. What we use is what's called the implicit hydrogen rule. What we're saying is, I will show you a structure, I will focus on geometry, but I'm going to focus on carbons. Instead of drawing C, 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 C over again like you're a preschooler, you use lines. Second, I don't have to draw hydrogens every single time. I know that the valence of carbon is 4. If I'm not showing you what is there, I can fill in the gap saying anything that is not shown, it's not a carbon, it's not a nitrogen, it's not an oxygen, anything missing to fill its octet must be a hydrogen. Yes?
Can you do a wedge dash structure without hydrogens too?
You could, absolutely. But and the thing is that there's a little bit of mixed mode here. So we could do this top structure here. So once again, let me go over to my things that would be totally cool. If I wanted to draw that structure like this, where I'm like, okay, I've got to have 3 fluorines over here, that's all right. I'm saying I'm using line bond structure. I don't have to show that there's hydrogens here, but I want to show there's 3 fluorines on this end. I could draw wedge dash, fluorine, fluorine, fluorine with no hydrogens showing here. Also cool. I'm showing that there's geometry, tetrahedral notation around that carbon. Things that will make Jason kind of mentally throw up. Oh no, let me do it this. Okay, I got my red pen ready. Please tell me 2 things that hurt your eyes on this structure. Yeah?
The fluorine geometry is impossible?
Yeah, what I'm trying to show here, I have no idea what you mean. Straight line like this means that bond is in the plane of the page. We're implying, what is the geometry of this? Do you guys remember hybridization? sp2, sp3, yeah. What is this? This is a sp, which should be what shape? What am I doing? Yeah, this is a complete, like, you have to come close. This geometry, what we're showing here, is a tetrahedral structure in a partially sort of perspective view. This is just nuts. Don't do this. What about this?
Has no reason to come out of the page.
It has no reason to come out of the page. What is this carbon is what hybridization? sp2. What is this shape of an sp2 center? Trigonal planar. It's flat. So why are you doing that? Like, you're somehow bending it so that this is in the plane, but that OH is not. It is taking this and actually skewing it out of the page. What I'm trying to emphasize is, if you start to do things like this is no different than you walking to McDonald's and saying, I have ketchup, hamburger, fries please, pickles. Like, I kind of get what you mean, but that could go a lot of ways wrong, okay? There's syntax, there's purpose for what you're saying. Okay, so the cornerstone of what we're going to go through here is practicing this part and making sure you're getting them correctly. In this structure here, practice the line bond structure from here. What I mean is go to the sort of zigzag type structure. What would this look like if you tried to take this kind of Lewis dot structure, and I've taken out the lone pairs just to kind of make it cleaner. But what do you think this should look like? Whoops. No. Sorry. There we go. That's the one. Okay. The way I do this, number one thing to do if you're starting out, number. And what we're going to do is number along the backbone of this. That provides sort of a linear series of molecules that are sort of the carbon-centric pieces, the main chunk of the molecule. I count them off. What that lets you do is transpose between different points. So not including the fluorine over here at the end, I have something that should look like 1, 2, 3, 4, 5, 6, 7, right? So it looks like this little zigzag type structure. Counting off our centers, that's 1, 2, 3, 4, 5, 6, and 7. Now what we have to do is match what functional groups are where. For example, carbon 1 has a fluorine. Carbon 2, just hydrogens. Carbon 3, just hydrogens. Carbon 4 has a double bond oxygen. Atom 5 is actually a nitrogen, so I'm going to switch that atom out. And it has a hydrogen attaching to it. Now you can use the implicit hydrogen rule for things like nitrogen as well. Usually we stitch it mainly, and you can start off focusing primarily on carbon. So since nitrogen is in the ring, it has one hydrogen, I'm explicitly going to show this as NH. 6 is a CH2, 7 is a CH2. I'm done. I don't need to do anything else besides this. The most important thing is, if I have a guy like this, a stick sticking out into space, that means what? That is what atom at the end of that line? That is a, yeah, that's a carbon attached to how many hydrogens? That is not just a stick, that is a CH3. That is what we call a methyl group. It is a specific number of carbons and hydrogens. Okay, one last one. This guy. As I said, start off in this, count off the centers, label them. That gives you sort of a disposition or a template to build up your molecule, and then you begin to draw it out. This one's a little more complicated because you've got these bonding guys in the middle. This comes down to the geometry, the hybridization of those centers. So I'm going to start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have these two groups. I'm actually going to leave those alone because they both branch off. There's a bit of a choice which way we go. Who's seen Sesame Street long ago? Still watches it now? 1, 2, 3, 4, 5, 6, 7, 8, 9. No? Sorry, it was my kid thing. You'll be starting to do this repeatedly in your head. Yes?
Why do you start counting from the oxygen and not the first carbon?
You can absolutely count anywhere you want, right? What I'm trying to do here is saying that I'm starting, just my convention, I start on atoms that are not hydrogens. And I begin to build the chain off of that. You can swap them in after. If you choose, starting on carbon, totally fine. But the point is, come up with a strategy which is continuous and repetitive. The way I like to do this numbering is that I know what the presentation should look like, and I know where the decoration should go later. But yes, you could start on carbons, no problem. So, if I have a 9-bond thing, I'm going to start and say like I did last time, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's just bang through this. All right, 1 is an OH, right? 2 is a CH2. 3, CH. 2, 4 is an oxygen. 5, CH2. Well, 6, 6 here is this carbon. Okay, but it's a triple bond. No problem, I'll just do that, right? I know. 7, that's the other side of that bond. 8, this is now part of another double bond. And then we have our 2 methyl groups, this guy and this guy, sticking off that end. And some of you did that kind of that moment. What's wrong with carbon 6, carbon 7? You can do it, you just shouldn't. What's the hybridization at carbon 6? Hybridization is sp. Remember, CH3 with something else, that's sp3. That has what shape? CH3 is sp3 is tetrahedral, right? This is sp2, right? sp2 is what shape? Trigonoplanar. This is sp. sp is what shape? Linear. This should be linear. That is not how you draw a linear structure. This should be redrawn through here as triple bond bounded to 2 others, right? So if I was going to redraw this structure, sorry, I'm going to have to pop over to my other one. Running out of room. So OH, 1, 2, 1, 2, 3, 4, 5. Nope. Like that. Yeah? And carbon 4, 1, 2, 3, that should be an oxygen, right? I'm going off of memory here. Is that sort of right? Most importantly, when I do this, in that circle, how many carbons have I circled right now? There are 4. There are not 2 with some weird lines. This is a linear structure of 4 carbons as a run. Okay, download the slide deck. Make sure you watch the videos. We're going to be doing the IUPAC naming after this. See you guys on Wednesday.